I think we have 2 minutes left, so I'll probably start introducing myself, and everyone else would like to start introducing themselves as well to get to know each other. So the EC community is a pretty tightly knit community. Of course, again, I'm pretty sure at the end of the day, once we graduate, we're all going to eventually know each other's names. So I'll go first. Hello, my name is Roberto Hernandez. I'm currently entering third year electrical at FIU, and I'm president of IEEE. Juan, if you like, go next.
Yeah, so I'm Juan Sanfiel. I am a former VP of IEEE, short-term president. So right now I already graduated as an electrical engineer. I graduated in December of 2019, and I am continuing electrical engineering as a master's student. And I'm working in one of the labs here, EPS, Energy, Power, and Sustainability. Roberto's had some experience in there. I mean, right now, I mean, if the school is open, I would highly encourage you guys to, go into there if you want to learn about renewables or anything about power systems or cybersecurity. Definitely, I would recommend that to you. But at the moment, since nobody's allowed on campus, they're not accepting undergrads. So I wish I could offer that to you.
Of course. Thank you, Juan. Whoever wants to go next for sure.
I'll go next. Hi, everyone. My name is Juan Saez. This is my last semester as a junior. I'm studying, I was studying electrical and I switched to computer. And I'm really interested in learning how to program like Arduinos and other embedded systems. I just got into that like these semesters, I basically bought this like a week ago. And yeah, I'm like really, I want to learn how to do this. And for instance, like I attended a workshop 2 days ago about this, and like the one that Miguel de Jesus hosted. Pretty good one, by the way. I really enjoyed it and learned a lot. And yeah, I just want to be more involved in the community and FIU projects and clubs and stuff like that. I wanna learn and I wanna contribute as well.
Beautiful, man. Thank you for that. Whoever wants to go next for sure. If you guys want to, of course, it's a mandatory. Whoever wants to go next. It's all good. Whoever wants to go next for sure, feel free.
My name is Tony Rodriguez. I'm actually a mechanical engineer. Not really an electrical. I just tend to do this for fun. I've been teaching myself about electronics for quite a bit now. I mean, I'm not super advanced in it, but I know like all the basics and how things work and how to put things together to make certain things. I also do 3D printing in my senior year, quote unquote. And yeah.
Perfect, man. Thank you. Would anyone else like to go?
Yeah. My name is Daniel. I'm a freshman in computer engineering. Nice. And I'm just really excited to go beyond what's being taught in the classroom to learn more.
Sure, man. Thank you. Appreciate that. That's the spirit right there. Perfect. Anyone else like to take the floor? We have quite a few people. Oh, a good amount.
Yeah, hi, my name is David. I'm in my senior year computer engineering, but senior is super mega quote. I'm in the 4+1. The only senior class I'm taking is senior 2.
Oof.
And yeah, for the master's, I'm focusing on computer architecture, design, and machine learning.
Nice, bro.
So I'm actually super interested in this PCB right now.
The future is very heavy on that, my friend. Anyone else?
Hey guys, my name is Miguel Sarabia, and I'm here, to learn, and I'm excited, to be a part of a group that we all share similar interests, where we can share ideas and and exchange knowledge, between all of us. So I think that this is really cool. So thank you for that.
Beautiful, compadre. Perfect. Anyone else? Final call. Feel free to, if you guys want.
Well, besides from this, what's going on?
Sure.
So I had a quick question to see if anyone knows anything about this. I know food dehumidifiers have been becoming a thing for drying filament, but because of that, the price of them have been going up. I don't know if anyone knows like a place to get them like for cheap or whatnot.
Instead of using dehumidifiers, I personally have a stash of silica beads that I use.
But I hear with like TPU and like nylon, even if you keep it with that, they still tend to absorb humidity.
I suppose, but I usually overdose on the beads, and I keep them in storage in like a nice O-ring sealed container. So it tends to work out for me. I don't have any dehumidifiers because I just don't like any amount of heat being put around the filaments. So I just rely on the passive effects of the beads instead. In my experience, they just work better.
I'll give it a try. Would you recommend?
But you need to make sure when you source your silica beads that they're scientific quality, they have high surface area. Don't go off like some eBay listing or something.
Okay. Any sites you recommend?
I have the ability to get deals from like Fisher and stuff. So I just asked my PI to get me them. So I don't know if a normal student has that capability.
No. I mean, I'll check around on like YouTube or like Reddit to see if anyone knows.
Yeah.
Perfect.
Yo, what's up, homies?
What's up, David?
Yo.
All right, perfect. Well, I think it's past time to start. A lot of people have joined. Thank you for those who just joined. We'll begin now. Perfect. Well, welcome everyone. I hope everyone's had a pretty great intro to their semester. It's been pretty rough. I know all of us will stay strong and hold on all the way to the end. I wish everyone's doing well and safe, of course. To start off, welcome to IEEE's third workshop of the fall 2020 semester. Today we're going to be talking, the first one was a microcontroller one. Second one, we had a Arduino workshop, and the third one was a PCB workshop. Thank you guys for joining for this, and we'll begin now. Perfect. To start off, before I get into concept exactly of what a PCB is, we'll talk a little bit about what are pretty much the early days of circuit design. So first of all, can anyone hear me clearly, by the way? Everyone good?
Yeah.
Perfect. Just making sure.
Yeah.
Thank you. So before I get into talk about what a PCB is and what it entails and what factors come into making a PCB, we're talking a little bit about the early days of circuit design. So back in the days in industries, factories, etc., products and different systems, you had a type of circuit design, right, called wire wrap or point-to-point method. And those were heavily produced and mass-produced methods to create circuits. So pretty much imagine you had a layout, correct? A plastic ceramic layout. That was the size of your composition notebook. Your average composition notebook size is about what? It's about 1 foot long and about 10 inches wide, right? That's about average size. And you could place your components there, right? And you connect them with wires. The thing is, back then, those circuits would work, but the wiring for those specific circuits, there were so much, you couldn't actually see the specific color of your layout on the bottom. So here, when you look on the left-hand side of the screen, right, you have a ceramic green layout, right? Obviously, you have some layers in the bottom. Some are plastic and some have some copper synthesizing material interiorly. But to get to the point, here you have a bunch of other components and wires going across. Here on the edges of this board, right, you can see the color green, of course, and the color of the actual schematic. But in the middle, right, if you look at it from over top, you couldn't actually see what color it was. And that was a huge problem. If there was an error here, it would take you probably hours or close to a day to figure out what was the error. Because the wiring was so much, it was like pretty much a bunch of electrical spaghetti. And it was just very hard to catch an error. Some of them weren't really sure they worked and they were efficient and they could be using the products way back then. But when it time to when you had to like change something or switch something out or just like I said, find an error. Back then, those circuits, those wire wrap circuits, were almost nearly impossible to fix. All you see is looking at the complexity. So what changed over time? Began, obviously, you had engineers and scientists working, obviously, in the labs and creating patents and stuff. They came up with a PCB design, right? Obviously, there were some mechanical engineers that came up with the materials and the ceramics to create your actual boards. So if you're an electronics lover, or you pretty much like or you pretty much think that electronics is cool, this would be a really great workshop for you.
We'll build a simple circuit. We're gonna build a 555 timer. So let's go on ahead. Okay. Okay. So I made this slide. I like it. It's funny. So what is a 555 timer? So basically, this is an oscillating circuit. I have the schematic there on the right. The link to the YouTube is right below it if you guys want to check it out. So basically, a 555 timer is an oscillating multivibrator. The purpose of this is to keep time in a circuit. In circuits, you have a clock, which it pretty much governs everything. Just like Bugs Bunny here, or Leopold, as they called him in that episode. Oh my God, it's Leopold. It's Leopold. So in that, the 555 timer is basically the maestro in an orchestra. Also, you can look at it as a drummer in a band. If the drummer is off or if the maestro is off, then the entire orchestra, the entire band is off. And this, you do not want that to happen in your circuit, because if one thing starts too early, if one thing starts too late, then you either have a buildup of current, you have a buildup of voltage. The current is too high and you burn something, or the voltage is too low and you can't start something. So really, you want to make sure everything is going at the same time. So the 555 timer is there to, just keep time, keep everyone working as they need. So yeah, I mean, the video is pretty interesting. It goes more into detail of what's going on. If you want to go into that, you can watch it on your own time. I just want to focus on, building the circuit for you. So the 555 timer has different setups. So for example, on there you see monostable, bistable, astable configurations. That just depends on what you need. That depends on your needs. So I'm going to show you the circuits that we're going to build in a little bit. But in the circuit that we build, you have inputs such as in pin 8. So the way that this is read, on the picture on the picture on the right, from the left side, the NE555N, there's a little circle on the upper left that just gives you a reference. That says, okay, that's the top side, and the left says, okay, that's pin 1. And then the way it's read is the pins go 1 through 8 in a counterclockwise direction. So left side would be, Roberto, if you could help me out here. Yeah, so left side of the timer, pin 1 would be on the upper left, and then you would go down in numerical order, then go across, and then go up. Yeah, so pin 2, then to pin 3, and then pin 4. So then you would go across to pin 5, and then all the way up to 8. So I know kind of like what a majority of these pins do, but not completely. So I'm just gonna go around the pins. So pin 1 is the ground. You're gonna need to ground to something. You're gonna need some sort of reference. So that's where your ground is. Trigger, that is something you'll learn in logic design for electrical and computer. Basically, it's just an on or off to activate the circuit. So then from there, pin 3, the output is, okay, where you're gonna, that's gonna go to the rest of your other circuit. Resets, I think that just resets the flip-flop. Let's see what else.
Yeah, it does. It does.
Yeah, control voltage. That one I'm kind of unsure, but it just, let's see, that pin 5 goes to, yeah, so between pin 8 and ground, pin 1, you have voltage dividers. That's why it's called the 555 timer, because there are 3 5 kilo ohm resistors in there. And depending on what you put on your peripherals, such as a capacitor or a resistor, depending on that, you're gonna have a time constant based on those values. So you can put a really tiny capacitor or a really big capacitor, and that's gonna affect the time constant. That's also gonna affect, okay, if you affect the time constant, you're gonna affect whether this multivibrator is gonna go really high frequency or low frequency. So let's see what else. Thresholds. I think that's kind of a comparator, but I'm not sure for certain. Discharge, that goes to an internal NPN transistor, which basically that controls when the voltage divider is discharged from VCC to ground, and then VCC is going to be your power source.
Yep, exactly. And the threshold pin is pretty much, it monitors the threshold pin of the 555 timer. It monitors the voltage like across the capacitor in the 555 timer that's like discharged at the 7th pin. So yeah, sorry about that.
No, yeah, thank you. That helps me out. So yeah, and the next one. Okay, yeah, so that's just so this is a pin out. Pin out just tells you exactly what the pins do or what their purpose is, and that'll help you connect your components, or at least know where to connect. So then the next one. Okay, so this is a schematic that we're gonna build. So I'm going to, let's see, share screen. Let me see if I have the, okay.
I put you as co-host, by the way.
Cool. All right. So I have my desktop here, so I can visualize this better. I'm also gonna see if I can try to have this visible at the same time, the PowerPoint. And okay. So here is my workspace. Let me go to the slide. Okay. So here's your workspace. So what we're first, okay, so I here need to put in a frame. So I'm gonna go to add part, and hopefully my computer is fast today. Of course, it's not responding. So in the meantime, while I'm, okay, yeah. So I need a frame here. So I'm going to, just to make sure everybody sees me, everyone sees the screen?
Yes, sir.
Cool. Yeah. All right, so A4 LOC. Place it here. Okay, so I'll press escape. So I'm done for now. Okay, so the cool thing about Eagle CAD, the mouse is friendly. It's mouse friendly, so you know, left click, you do what you need. You click wherever. Roll click, roll. You can zoom in, zoom out. If you click the roll, you're able to actually move this. Let me see. And then right click, you're able to, once you get a component, you can see the properties of the component. Let me just check the chat. Looks like it was a little active. Nice, David. Okay. So yeah, now let's add a component. So we're gonna go, I don't know exactly which library to go to. So I'm gonna do what I mentioned before. We're gonna press asterisk 555 question mark. And then here you're able to look at, these are gonna be the possible options. Like, okay, I saw you put this, here are the possible options if these are the right ones. So I'm gonna pick this one, 555 timer. You can click here, right, this triangle to expand, and they show different 555 timers. So you're able to see on the left, this is the grid schematic view. And then here, this is the, there's a name for it. This is the footprint right here, the footprint. So here this is the name value, this is the name, this is the value. If this was like, let's say a resistor, this would be you can put 10 kilo ohm resistor, 20 kilo ohm resistor. That numerical value would go right here. So this is a surface mount 555 timer. Basically, these are the ones that look flat on the board and have no, they don't go through holes. So here, this is the one we're going to be working with. This is a through hole 555 timer. I'm trying to think back to a circuit that we use a lot. I think it's the 741. I don't remember exactly what it was.
The op amp?
Op amp, yes. Yeah, so a 741 op amp, that is a through hole component because you're able to put it into a breadboard, and then it'll go into the holes and it'll stick there. So you can use that same op amp with a through hole configuration. We're going to do the same thing here with this timer. So when you go to print this out, it'll come with the holes already done. All you have to do is just put the component in directly, or you can put a little, I don't know what the name is, but it's a little thing of pins that goes into the same holes in the board, and you can put your timer on that. So that way, if you need to replace the timer, you don't have it already soldered into the board. You can at least leave the little tray or whatever it's called, the little adapter where it's connected. It'll still be there. Just change out the old one, put in a new one. I'm just gonna go through the rest of these so you can see how they look. That's another surface mount. Oops. Another through hole, surface mount, through hole. Yeah, so they have, different configurations for different components. Just make sure when you have the actual component that you find in the library the one that fits for that one. So I'm gonna go click OK. I'm gonna place it here. I only need one. So then we're gonna go look for some resistors. So here we're gonna look for RCL. So that's resistor, capacitor, inductor. Okay, yeah, so here, sorry, no match. That's what happens if you look for, it's gonna look for these exact words. So let me see if I can clear this. Click OK. And then the entire library should show up. So we're gonna go into the library RCL. And all this is in the slides. So if you get lost here, I'll help you out now, but if you get lost here, if you want to do this later, everything's in the slides. So here, this is in alphabetical order. You have capacitors, inductors, and resistors. You have CEU, so this is for European models. There should also be CUS for US models. Let me see, chat's a little active. Okay, socket. Yeah, so the socket is what you put in place of the actual component to have it there, and put the component, take it out, put it back in. So we're gonna look for US resistors. So we can open here, press the little triangle, get all these. So this is how it looks on the circuit, and this is how the actual footprint is gonna look on the PCB. So just gonna go through this so you have an idea of potential footprints. So again, this depends on the type of resistor you have, the size of the resistor you have. So you just want to make sure that the physical components that you have, you find the correct footprint. So here, these are through-hole resistors because you have the pin. If you can put in a breadboard through the holes, that's through hole. And this one here, this is a surface mount resistor. These are very small. They're a lot harder to solder because they're so small. You got to be very careful. It's best if you have a machine do it for you. Another surface mount. So just to show you guys. So yeah, when you have a through hole, it's gonna make a hole for you on the PCB. If you have a surface mount, it's gonna leave you a piece of copper, and that's where you solder this and this end, and then that's where the contact is made. So there's a lot more. We're gonna use the through hole. Let's see. And in the okay. Let me go back. I believe in the new version of Eagle CAD, it's able to show you the popularity of each component. So you can see if it's a component that's highly used, it's most likely you could use that one, or it'll be good for your uses.
Yes, and it's also really, really accurate with the tolerance value specifically also.
Yeah, I'm gonna turn the light on in my room, so just give me a moment. Okay, so for this schematic, we're gonna use 4 resistors. Let me zoom in here. We're also gonna use 2 capacitors. So I'm gonna escape. So we're gonna go to CUS. So again, here is the schematic symbol, and here's what it would look like on the PCB footprint. So these are different sizes for different uses. Okay. Yeah, and then here are the surface mounts. These are very small capacitors. Okay, so let's go with one of the first 2. I'll probably go with this one. Okay, so 2 of these. And then 2 LEDs. So I'm gonna go back, I'm gonna escape again. Is anyone stuck yet, or is there any questions? Cool, I like silence. Silence means yes, we're cool. All right, so then LEDs. So to avoid looking through this, I'm gonna type LED. Okay. And then it gives you all the options here. So I'm going to go to LED here. Again, this is the basic schematic. And here you have a bunch of options. Like, there's some cool stuff here. So these are surface mount LEDs. I've never worked with surface mount stuff. That would be cool, but I don't have use for that at the moment. Hopefully sometime in the career, maybe. There's this one that had like a central one with like 6 LEDs on the outside for the perimeter. That looks really cool. Let's see. Yeah, so here you have LED strips. Eventually I'll find it. Okay, so the LED that we're gonna work with is this one. So the two green circles, that is the circles that are gonna be made on the PCB. And over here, this little gray stuff, this is what you would see if you were to look from the bottom portion of an LED. So here you have the flat side of the LED, which would be here. And so that tells you that this is, so I get my anodes and cathodes confused. I believe this would be the cathode here, and then this here would be the anode. So this flat end gives you this reference here. So
the anode is a positive one, right?
Yes.
Yeah, bro.
So we're gonna get one of the two of these. Sorry, 1, 2. Okay, and then we're gonna have a battery added to this, so we can type battery down here. So this is in the battery library. I just closed it, open it again. So we're gonna look for a 9-volt battery. So I mean, you all know what a 9-volt battery looks like. This is the schematic view for it. This is what it will actually look like on the board. So we're gonna get one of these. So I want here for it to look vertical with the positive sign pointing up. So what I'm gonna do is I'm going to rotate it, but I don't actually have to come over here to rotate. I can Control R. If you press Control R, oh, I guess you have to set it down first. So you have to set it down first, escape. I'll just close this. So when you want to select a component, just click on it. It'll turn bright red. So just to demonstrate to you. And when you select a component, if you want to move it or anything, there's this little plus right in the center. All the components have them. The resistor has it here, resistor has it here. The capacitors have them right here, but you can't see it in the thick red. You can see it right here. And the labels have them too. So if you want to move a label, you can do that. But I'm going to Control Z that. So this, I want to rotate it such that this positive is at the top. So when you select something, right now it's a dark red. Now it turned into a lighter red. I'm going to rotate it. I'm going to demonstrate here. Rotate. Let's see, what didn't it rotate? Oh, okay. So I had to actually click it. I actually had to click rotate and then click the component. And then now I'm going to do Control R. Doesn't do it like that. I guess not. So yeah, just use the rotate and then click the component. Okay, so pretty much we have everything right now. So then we're gonna have to connect. We're gonna have to connect everything. So I'm just gonna start putting things in place, and you guys can follow along. So I'm gonna leave R1 here. R2, I'm gonna put it over here. R3, I'm gonna put it up here. R4 will come up here. I'm gonna put one capacitor down here. One capacitor over here. And for my purposes, I want to have the capacitors vertical, so I'm going to rotate them as well. And I'm going to select multiple. So I don't know if you can group them. Like if you group them, then it will include this. So I'm going to see if I can shift click. Let's see. Okay, so I'm gonna, yeah, so you can shift click and you can individually select what you want. Shift click. So I want to rotate my resistors so that they're vertical. So I'll just click them. Oh, I guess that didn't happen. Oh well.
I think you were supposed to press the rotate button first and then click everything.
True. Oh well, I'll do it individual. Okay, and this one too. Alright. My capacitors are vertical, my LEDs are vertical, so okay, I don't have to rotate anything else. Alright, so then we'll start connecting stuff. I have the, oh, look at that. Let me escape so that, yeah. Alright, so I have the schematic open on my desktop. Since we're on screen share, you can't see my thing. But I'll connect it as I have it here. So we're gonna go with, okay, in the way I have it on my laptop, it's the configuration of this was different. So I'm going to rotate this. Or actually, I think I'm gonna mirror it first. So I'm gonna mirror, which is this one here. Click it here. So then everything went to the other side. And then I'm going to rotate it. And again, you guys don't have to do this, but this is just, you know, this is just for my purposes. Okay, so now we're gonna connect this R1 is gonna connect to R2. So I'm gonna move R2 so that it's right in the same line. And then I'm gonna go to net, is the green one right here. So then when you have a net, you go to the end of your component and the bubble shows up. So that means you can connect here, move down, and click here. So yeah, every time I move, I move with the center scroll. I click the center scroll and then I'm able to move around. Okay, so then from there, between R1 and R2, I'm gonna make a junction using pin 7. So I'm gonna zoom out, pin 7. I click, and then come up. And then once you click here, you can make a junction. And then there's your junction. So what is also required, this capacitor is going to go under R2. So I'm going to move this. I have to escape. Okay, move this. So I'm going to grab the capacitor right here. Again, you can't see the plus. If you grab this plus, they're going to move only the label. Okay. Net from here to here. Cool. All right, so let's see what else. All right, there is this capacitor here, we'll move it over here. Just so I'm saying everyone is following along or nobody feels behind. I'll take that as a yes.
Yeah, bro, all good, all good.
All right, cool. All right, so then for this C2, we're gonna connect C2. Let me open it up here so I can see better. C2 connects to pin 5. So we're gonna net C2, 2, and 5. Okay. So then now we're gonna work on these resistors. We'll move them over here. Cool. So we'll net them together. Okay, so between these resistors, they connect to pin 3. So we'll net that. So remember, you can click and then turn 90 degrees. That's your next junction. All right. And then we're gonna have one LED above R3, and then the other one's gonna go below R4. We'll net them together. We'll move this. Connect that. All right, so I believe the components are connected. So now we're just gonna be connecting the pins. Some pins connect to other junctions or other components. So we're just gonna make those connections, and then from there we're gonna be adding the ground and the VCC. So right now, let's see. We can connect pin pin 6. So pin 6 is gonna go between R2 and C1. So it's gonna connect right there. We're gonna net. And then pin 2 is also in junction right here. All right, we got pin 2. Let's see, so. Okay, so we pretty much made all the connections that we could without using the ground and the VCC. So now we're gonna install that. So we're gonna go to part. We're gonna type in VCC. We're gonna search for that. So here are different symbols for supply. You can use any you choose. For our purposes, we'll use we'll use this one. So in the schematic that I have, we have 1, 2, 3, 4 of these, and I'll put them right next to where they need to be. So we're gonna need a VCC. So VCC is pretty much your source input. So you're gonna need one right here. So that's gonna be the positive side of the battery. And then this is gonna go to this R1. Is also gonna go to pin 8 directly, because remember this is V positive. So I'll put this right next to it. and then the VCC for the LED and the resistors. So this VCC is the same throughout. So pretty much, so when you look at it here, they look like they're all over the place, but really it's the same connection. Just like how when you draw a circuit, you have the little ground arrow. Even though the ground arrow may be one over here, one over here, one over here, it's all the same ground. So this is pretty much the same thing with VCC. It's all the same VCC. This is 9 volts here, 9 volts here, 9 volts here, and 9 volts here. So we're gonna net them together. So battery's connected. Then R1 is connected to the battery. Pin 8 is connected to the battery. And then the LED is connected to the battery. Cool. So now, just like in all circuits, we need to ground everything. So we're gonna go back to add part. We're gonna put G and D for ground. Again, they have different symbols for grounds. They all do the same thing. So for this one, I'm gonna choose this one. So one for the battery, one for the capacitor, one for the LED, and yes, we have only 3. We'll connect to those. So connect that. Okay, so yeah, I mean, and this one is, oh, it's a 4th ground. I forgot that one. One more ground for this C2. I'm going to rotate that and connect it. So pretty much we have our circuit done. I just want to make a simple circuit so it's easy for you guys to follow along. So yeah, this is something that, you know, the electrical engineers see. It's pretty much like the AutoCAD of circuits. You know, you see the plan before you actually see the physical thing. So now that we have this ready, I'm gonna save this one just to make sure it doesn't go away. Okay, so I'll call this IEEE 555 timer. Save.
Do you think we can make this with just one layer?
I mean, I don't look into the layers much. I pretty much work in what is already given to me because it's the simplest. But can you go a little bit more into your question so I understand it better?
I don't know if we're gonna get into like designing a board, because right now we have the schematic, right?
Yes. Yeah.
So yeah, I don't know if you were gonna do it with 2 layers or just 1 layer. That's all.
Yeah, so when I do it, I pretty much do it as is. It's easiest for me, and
Okay.
and unless it's, you know, specified that I need it, or if it's something I do need, then I would consider it. And actually, yes, now that we've finished this, wait, let me see. Oh, I forgot to connect pin 4 to this VCC up here.
I think this one would probably have a good like 5 layers, like the mechanical layer, the keep out layer, the overlay layer, and like your overall like soldering mask layer. So I think a good 4 layers this circuit will probably be as we would have printed out.
Thank you. Bye, Naima.
Gotcha.
All right. Wait, pin 1. All right, because I grounded it right now. Okay. Pin 1 is also grounded. Can't forget that. Okay, let me go I'm gonna check my PowerPoint just to make sure I have everything connected because you guys are following me. Okay. So battery connects to VCC, connects to ground. We have our 555 timer. Pin 8 goes to VCC. The threshold comes down and it connects between R2 and C1. Pin 7 connects between R1 and R2. Pin 3 connects between R3 and R4. Pin 2 connects into this junction here. Pin 4 goes directly to VCC. Pin 5 goes into the capacitor. And then pin 1 goes into the grounds. And then the capacitor is grounded. Okay, so then R3 is connected to R4. R4 is connected to LED2, and LED2 is grounded. And then LED1 goes to VCC. Okay. All right. If I was able to know how the simulate works, I would do it. But let me just see something here. You're able to put an ammeter and a voltmeter onto your circuit, and it won't show up on the actual PCB once you go into schematic, once you go to the board. Here, so voltage probe. At least with this, you're able to, like, let's say, click from here to here. I mean, you guys don't have to follow me with this one. I'm just playing around with this. I'm gonna do that. And pretty much here is where you would go for the simulation stuff. So this is the button to simulate. Sim results toggle. There's probe, add model. Yeah. Roberto, if you can remind me to include, if you can give me a little reminder just to get the Eagle CAD video, so I can send it to you, and then you can send that to the other students so they can see what I mean.
Perfect. Sounds good.
Yeah. So now we're gonna go into a schematic to generate board. So this will come up the board. We're gonna pretty much make a schematic. It doesn't exist yet, so we'll click yes. And then that'll take us to the actual PCB board. So this dark area is gonna be the area of your PCB. And here are your components. All the connections that we made have already been done. So I'm going to group, and that was left click. I'm gonna move. Hopefully I can move everything. Nope. Escape to clear all that. I mean, it happened to me before where I picked up everything at the same time, and I don't remember how I did it. Just so you don't have to go one by one, moving everything. I guess I'm gonna have to do that. Okay, so let's start putting things over. And I mean, if you guys were able to do it in one shot, kudos to you. Okay, so this is a lot of area for our PCB. We're gonna shrink this down. You don't see my screen? Let me see, I'm still sharing.
Maybe it's frozen?
Yeah, it kind of crashed.
Huh.
Maybe close it and open again, like the screen share.
Okay, let me stop share. Okay, let me go back. How about now?
There you go.
It's fixed.
Okay, cool.
There you go.
All right, so just to point out here, this is your reference area. You do not want to move this because this is what the PCB etching machine uses as its reference. So pretty much, you don't want to touch that unless you have a lot of experience with this. You know exactly what you're doing. Then yes, you can mess with that, but really you don't want to.
On the right, I see that it says Fusion 360. Is that what you were meaning at the start of the workshop?
On the right, can you? I'm moving the mouse. Can you point me?
On the right, almost where you have the scrolling thing. Below manufacturing on the right. Well, never mind. There.
Oh yeah.
Yeah.
Yeah. Yeah. So let me just make sure I'm escaped. Okay. So we're just gonna shrink this down because you don't want a large piece of board just for a few components. So you don't need to click any of this. Just click right here. And then this will just make sure it's square-ish. I mean, I'm moving this here, but you want to try to keep it as square as possible. So now we'll zoom in. Here you can look at all the zooms. Zoom to fit. So now that we have this here, we can move this anywhere we want, and we can also orient it. I like to have my 555 timer with this part up, so I'm going to rotate. And even if you rotate, the connections are still connected. You don't have to worry about that. And I want to have it in the center. The battery, I want to have the positive side to the left, so I'm going to rotate that. Cool. And I want it to the bottom. And you can, one moment. So I want it as close to as possible to the bottom, but there's a little hassle here. I have my G1 sticking out, and this G1 is a layer. Oops, I flipped that by accident. Let me mirror that. Okay. So this is going to be something that you can actually read on the board. It's going to be like printed white on the board for you to know what's going to be going there. Just like this AB9 volt. So that helps you once you go to connect it, you see, okay, this is the 9-volt battery. This is what it tells me. This is G1. Oops. Move that. And you can put it wherever you want. Okay, let's see what else. Okay, so I'm going to rotate all of my capacitors all of my resistors until they're vertical. Okay. And one more. Yeah, and you see this? So this is telling you that if you were to give this to a machine right now, it would drill a hole here, but you have an error here because you're drilling pretty much on the edge of your board. So you don't want that to happen. So you just want to move so that you're within the perimeter. Okay, so I'm going to put 2 resistors on each side. All right, Tony, thank you. And then I have an R3 here, just to line it up, and R4. Okay, so then I want my capacitor 1 and capacitor, I have to make sure I get this plus here, capacitor 2. I want them up and down. And then I want LED 1 over here, and LED 2 over here. And again, this is your board. You can put it in whatever position you want. These are my preferred positions.
Are you gonna auto route it?
Yeah. So I wanted to show the different ways to connect it. Let's see. I was just waiting for this chat. Okay. So then, right now, the configuration of the connections was as it was over here, but what it is now is that we move things around. The connections are still there, but they're not in the most optimal position. So what we're gonna do is we're gonna do something called rat's nest, and it's just pretty much gonna make these connections as short as possible. It's gonna be the most efficient, and there you go. So now that we've rat's nested this, we're able to connect it. So here, I didn't put the 2 columns in the slides for this, which I should have. But really, these are gonna be your most important tools here. So here is the route. These route your vias. That's what they're called. When you have a PCB, the little copper trace has a via. So that's the name of it. So here you have the red connection. So this is when you go to print, this is what the PCB will actually print. It will create the hole here for the through hole, and then from there it'll follow this path exactly to your next connection, which in this case is this pin right here. And the C. Oh, now I'm just playing with that. Okay, cool. So right now, this right here, I'm gonna click the scroll. When you click scroll, it makes a small hole that goes. The red is the top, is going to be the top layer via. You click here, and then here you have a blue. This is the bottom layer via. So let's see. I have an actual PCB board. Let me see if I can find it. I'll be back in like a minute. So you're able to make vials on the top and bottom of your board, just in case you need more space or more surface area. Yeah. So in this case, and I don't know if you can see it here. So here, this is another PCB that I've made. And here, this is the top side, and then this is the bottom side. Let me see. I'll probably have to turn on the light for this one. But there are some vias right here. Yeah, I'm about to turn on the light, or I have to have my phone. Yeah, so that little line there is a bottom via that just connects to different points along the board.
It helps you to move between the top and the bottom layer, right?
Yeah. So if you want to create a top via, it'll do it automatically. Let's see. Okay. But I'm gonna just stick to that. I'm gonna Control Z. Okay. So yeah, just to make one simple connection, you can go to here, change. I don't know why that happened, but either way, I'll just go with this as it is. Okay. And then for the second one, yeah, so what happened in the first one is it started off as a bottom via, goes to this hole, and then comes out through the top, and then connects to here. So then I'll connect another one just so you guys have an idea of what it looks like. And I discovered this right now. You can play with the right click, and you can see how the mouse, the connection changes. And this connects to here. And then one more so you can see how you see it now is what I'm used to. So I'm gonna right click, just so it doesn't look so, robotic, aesthetic. Okay, and then yeah. So now what I'm gonna do is I'm going to auto route it. Low effort, makes it as efficient as possible. Run through all the possibilities. As you see there, it's looking like Doctor Strange right now. And I'm not going to evaluate it. I trust it. End job. So pretty much that is the most efficient routing that you can do. And I know I'm already almost out of time, but I just, have a little bit more to say. Oh, by Assad. And pretty much you are done with the PCB. So what you can do, I'm going to save it and go to, so what you can do now is you can export this file. So you're going to go to File, you're going to press OK. I'll put this on my desktop just so it's easy for me to find, and then save there. So when I go to desktop, So it creates a zip file that you can upload to. Okay. Did you guys see me, or what was it showing the screen?
We're still on the Eagle CAD screen.
No, yeah, because it said that the screen share was paused. Okay. Okay. What are you seeing now?
We're
Actually,
still
Eagle
on
CAD.
yeah.
Okay. Let me. Okay. Yeah, because I'm sharing on this screen. Okay. Let me change new share. This one. Okay. So I saved it to desktop, and it's right here. So what you can do now is you can go to a website that is for making PCBs. So I believe JLC is one of them. Okay, so I believe I already have I have an account on here. So if you don't have an account, it's free to make one. Okay, so Jason. Right, how can I forget? Let's see. Gotta love robots. Really?
Yeah, you missed some in the background.
I hate doing this, man.
Okay, it looks like the last time I actually entered with Google. So when you upload your PCB board, it'll show you a rendering of what it'll actually look like once it's printed. Okay, so you can go into my file. So I've already uploaded one just so I know how to do it. Okay, so here you can add one. So I'm gonna show you how you can add it. And again, everything that I explained up till now is in the PowerPoint. So this is included there. So it says attach your Gerber file, zip or RAR. So Gerber file is the file that we just made. So just waiting for this. on this PC. So I know that I'm already over time. In the PowerPoint, there's also another schematic. There's another schematic that I wanted to do had we had the time. But if you guys want to make it yourself, you guys can do that. So let's see, date modified. This one, open it here. So now it's gonna load. So this will show you the, my thing is sensitive, okay. The front and back of the board, and that's how it would look like once you go to print it. Usually when you go onto here, it gives you, these are all the parameters that you can change. And I think you have to order at least minimum 2 or 3, because if you go to print it, or you print it and let me see, PCB quantity, yeah, minimum is 5. So if you go to print it and you make a mistake, you want to have backups. So pretty much that's what I wanted to demonstrate to you all. I don't know if Roberto one day will have a QScribe demonstration, but pretty much everything that we've done here can be uploaded to the QScribe. That's at the campus, so I doubt it'll happen anytime soon. The QScribe will be able to etch this out, but yeah, I mean, this is something that you guys, just to make sure that it works for sure, send it to these websites, and yeah, you guys can get it from here. So I'm gonna give the screen back to Roberto. So I'm gonna stop share here, just so he can continue on to the PowerPoint.
Yeah, I think we are a bit past time. Do you want to continue on the PowerPoint, or if you want, we could do this a smarter way. We could create a part 2 for a week and a half from now.
I don't know if I'll be able to give a part 2. If anything, I'll go through the slides quickly, and I won't go too much into it. Yeah, because we're almost done.
It's all good. It's all good. Let me share the screen. Perfect. We're here. We just finished this one.
So we are right now slide 57. Yeah, keep going until it says let's make the next one. Okay, that one. Okay, so we're not going to do this now, but you can make an AC/DC rectifier. The one that I showed you right now is an AC/DC rectifier PCB. So yeah, so I'm gonna, in the next slides, it explains what it does. So Roberto, yeah. So I actually use this for my senior design project. So I'm assuming everybody here has taken circuits. So what this does is it gets, okay, so I might need to go back and forth in the slides, but I'll try to keep that at minimal. So here we have the inputs. What the inputs for here is an AC sinusoidal wave. And this is V positive, V minus. And I use V positive and V minus because there is no ground in AC unless you're dealing with 3-phase power and all that. So you're gonna have an AC input come into here. This is a full bridge rectifier made with diodes. You can have a full bridge rectifier already made in one component, but for our purposes, it was simple. So you have 4 rectifiers connected in this manner. You connect one portion of the AC here, portion of the AC here. This rectifies this into DC, but it's not going to be completely smooth. It's going to be a little bit choppy, and you'll see that in the next slides. So 1 is the input, 2 is the full bridge rectifier, 3 is an RCR filter. CRC filter. So basically, the capacitor is there to smooth the voltage, along with the resistors, just to just drop it a little bit. Really, you want to keep the resistance as low as possible because that'll mean you have less power at the end. So yeah, smooth lowers the power a little, smooth, lower, smooth. And then here I added a ground because now we're already in DC. So you have to ground it. And then this right here is a voltage regulator, 5-volt voltage regulator, which we used for to power our electronic equipment. And then here is the output. And then you connect whatever you want to here. So our senior design, we try to make a bicycle with a dynamo. So the dynamo inputs to here, runs to this, and then it powers our equipment, which runs on 5 volts DC. So then in the next slide, you'll see more of what I'm talking about. So yeah, all the numbers that I put in the previous slide is here: AC input, full bridge rectifier, RC filter, 5-volt voltage regulator, and then the DC output. So here in a natural AC wave, you have a smooth sinusoid, but you want to convert to DC. So once you run it through the full bridge rectifier, which was the diodes, you're going to get what would be the half wave, the positive half wave, negative half wave. You've rectified it to positive half waves all the way through. So this is now up here. But this is not a DC, this is not completely DC because DC is smooth all the way. So you're going to have choppy bits here. And then, so here you have a voltage rise. It starts to fall. It falls until here, and then it rises again. So it's going to be not a smooth, I was going to say like a jittery signal, and you don't want that. You want to have as smooth as possible to have a DC. So the smoothing allows this to happen. But then the 5-volt voltage regulator really the filters gets it more smooth, but the 5-volt regulator gets it to the voltage that you want it to be. So in this case, it's 5 volts. So yeah, in the next slide. So yeah, this is the schematic already done in Eagle CAD. This is the next one is the board view. So this is the board that was already printed. So this is what I meant about having a small setup. So everything is able to fit right here. You don't want to have a large thing, unlike one that was in the older slides. And the next one, yeah. So that's pretty much everything I wanted to show you today. If you feel like it, you guys can look at this schematic. If you want to build it yourself, great. If not, at least you learned something. And yeah, I mean, I'd like to thank Roberto for telling me about this, giving me the opportunity to show you guys, get this knowledge out there, for some freshmen, starting from freshman all the way up to senior. This is going beyond what you're learning in classes, and really, they don't teach you this stuff until like masters, because really, when you're in undergraduate, you're just there to learn how to use the tools. You learn how to use the MATLAB, how to use multisim, how to use whatever. But really, the real education comes from when you do stuff yourself. And I'm just glad that Roberto gave me the opportunity to show you guys this.
Of course. No, thank you, Juan, for coming, man. Yeah, I think, like I've been trying to tell and trying to introduce at least a workshop or two every week until probably the semester ends, and hopefully until next year as well. It's been a rough time, and it's been a lot easier to do virtual events, of course. You get me?
Yeah.
Yeah. Of course.
So if anybody has any questions or just any interest, anything you want to add?
You made that design for the AC to DC by yourself?
Yeah, I mean, I pretty much took what I learned from circuit analysis, and really it was just a simple problem that we had to solve. So let me see if I just want to pull it up because now I want to brag. So our senior design was called Genlock. It was a bicycle. It's like something you add to your bicycle that it's really not in the way, and you're able to lock your bicycle and also
leave it open. I sleep like that.
Power your lock on the go. See, so yeah, this here, this was the dynamo. It went on the front wheel of our bicycle, and it creates AC. And there was no way that we could find a dynamo that generates DC, so we had to convert the AC waves. So yeah, let me see, it's a video. So these were the actual waves that we were getting when we would turn the wheel, and that is not, I guess, conducive to what we wanted, because we wanted to power an Arduino, and Arduinos run on 5 volts DC. And actually here we had that little thing right there. That is, yeah, all the components connected to it. And then we had a little housing here. Okay, we had a little housing that goes onto the frame of the bike that goes in between the user's legs. So we had that 3D printed actually in the IEEE lab. My 3D printing skills at the time were not the best, but I did learn a lot. That took many hours to print. So those little curves here, that would go onto the frame of the bike right between the user's legs. And then on the inside, which will come up, yeah, there all the components would fit, and then it would have the those holes are for a USB, a regular USB input, and then a micro USB output. So that's for when you want to that's so you can charge your phone in the upper one, and then in the lower one you can charge with a regular charging cable, connect to the wall, and then connect to the micro USB on the second one, so you can charge the internal batteries through there. So yeah, basically this here was just to get the power from the dynamo on the wheel to the batteries in that little box. So at least
you don't have to charge the module at all. You just charge when you ride the bike, right?
Yeah. Yeah.
Cool, bro.
Yeah, I mean, I really liked. I mean, I like, senior. How do I say? Senior's experience. It's a lot of writing. But if you like the project you're doing, it's one less thing that makes it, how do I say, burdensome.
Cool.
All right, Bill. Thanks a lot for the workshop.